All right, finally, we're at chapter 11. This is the end, the last chapter that we're going to cover. This is about planetary systems. The beginning of this chapter is about our solar system, and the rest of it is really about the what are called exoplanets, planets around other stars. And just to let you know before I even start this, we if you go back 40 years ago, we did not know whether there were planets around other stars. We assumed there were, but no one had actually detected any because the technology just wasn't there yet. And I'll explain what happened in the early 1990s. All right, so this first part, this is stuff we've already had about planetary systems. So I'm going to try to go over this quickly. All right, so this is just a an artist rendition of a planetary system which is still undergoing formation. One of the things that we find, and we can actually see pictures, or actual pictures of star systems forming, and there's these regions where you can see there's these regions that have been cleared out at least slightly, where you can see through the disk of material. The disk is already flattened out. It was originally somewhat spherical, and then as soon as it begins to rotate, it takes just a short amount of time for all the material to flatten out into a disk. That's called the conservation of angular momentum. It's something we understand quite well. All right. So anyhow, that's that. All right. For centuries, planets were only known to exist around our sun, and it's very recent in human history that we discovered planets around other stars. Like I said, we always imagined that there would be other solar systems out there. Um, all right, so in our solar system, of course, we have the inner rocky worlds, the rocky metallic worlds, and then the outer planets, which are gaseous, and also known as ice giants, right? For in the case of Uranus and Neptune. All right, we have actually measured this, that the solar system formed about 4.5 billion years ago using radioactive dating. We from meteorites and from different samples of the moon and samples of Mars, that indicate that our entire solar system is 4.5 billion years old. So the big question is our solar system typical or is it unusual? So when we go out and we find these other solar systems, are they going to be exactly like ours, where the rocky metallic worlds are in close to the sun, close to their star, and the gas giants are out further? A quick answer is no. This was one of the big surprises. All right, so we'll get back to that. So this, is, of course, is when you think about it in terms of mass, like 99 point almost 99.9% of the mass of the entire solar system is our sun, right? It's an incredibly massive object, even compared to Jupiter, right? Which of course is the biggest planet, the most massive planet. Everything, all the energy, everything is centered around the sun, as far as our solar system goes. The orbits are, of course, we know that they're elliptical, but they're really close to being circular, right? That's in fact why 400 years ago it was so difficult for Johann Kepler to figure this out, to figure out that that the planets travel in elliptical orbits. All right, so and then of course when we go out beyond the ice giants. I'm sorry. Before we get to that, between the rocky worlds and the gas worlds is the region called the asteroid belt. Right. So this is and there is Ceres, Pallas, and Vesta, which are large. Originally, they were considered large asteroids. For a while, just to let you know, in the 1800s, they were actually considered planets because they were circular. They orbited the sun. It was only later that they were classified as asteroids when a bunch of other asteroids between Mars and Jupiter were discovered. And then later, really very recently in the 21st century, they were fully reclassified as minor planets. So they're considered minor planets. I mean, they were called that before, sometime before in the 20th century, but it became official right around 2006, actually. And that's right when, of course, Pluto lost its status as a planet. I mean, so anyhow. So beyond, and so that actually brings us to the Kuiper Belt. Pluto is the largest member so far that we know of the Kuiper Belt. It's one of the, but of course it's a dwarf planet, or also known as a minor planet. So you know how within the asteroid belt, you have, of course, asteroids, but that's between Mars and Jupiter. But beyond the orbit of Neptune, this is somewhat limited to your textbook. These are called asteroids, which I think is kind of cute, but I don't know if this name is really catching on very well. Anyhow, so that's the Kuiper Belt. It's still more or less within the plane of the solar system. And then outside of that, so way, way out. So the Kuiper Belt goes out maybe 100 astronomical units. We don't know exactly how far. This picture is showing it going out to about 50 astronomical units. But, easily it could go out to 100. But then beyond that is this region around 50,000 astronomical units from the sun. And that is a spherical region called the Oort cloud. All right, so this is all, information that we already talked about in chapter 10. Let's see, the inner planets and the outer planets each contain 4 planets. Of course, all the planets orbit the sun in the same direction, and it's the same direction that the sun spins, counterclockwise when you look down from the north. Right? It depends on which way you look at it in space. But if you were above the solar system looking down, everything is going around the sun counterclockwise. The sun is spinning in a counterclockwise manner. All right, so planets lie very close to the same plane. That's why you find the planets along the ecliptic, which of course is defined. Well, it's defined by the path of the sun, but it passes through, of course, the 12 traditional constellations of the zodiac, and also remember between Sagittarius and Scorpio, there's a region. There's a constellation called Ophiuchus, where the sun's not in Ophiuchus for very long. It's only about a week each year, but it does pass through that 13th constellation. All right. Anyhow, the point is that all the planets are more or less in this flat plane, whereas the Oort cloud is this spherical object, and the reason that we think the Oort cloud is out there is because you get these comets that come towards the sun at these huge angles, and the only way to explain that is with this spherical Oort cloud. All right, so this is just showing you our sun, our solar system. Of course, Venus is a little bit of an oddball in that it's spinning clockwise, So it's actually sometimes people call that retrograde rotation. Um, Uranus is spinning on its side, so it's tilted a little more than 90 degrees, and the same thing with Pluto. It turns out. Um, all right, so yeah. So when you look at the moons of the planets, especially the large planets, um, the gas giants like Jupiter and Saturn, of course, the moons seem to be little mini solar systems in and of themselves. And sometimes there's even like a captured asteroid or two. All right, so let's see. The composition of the inner and outer solar system very dissimilar in appearance. The inner region, of course, is this rocky world. There's lots of asteroids. The outer region contains gas giants and small icy bodies, also known as comets. Um, all right, so this, the idea is for the formation of our solar system is that the more dense material ends up close to the sun, the less dense ends up further out, and then further out, where the gas giants are, or where they formed, there was a lot more material. The material, of course, being the original gas that formed the solar nebula. The gas cloud that formed our solar system. By the way, it's very likely that our solar system formed, and many solar systems formed at the same time from the same original gas cloud, because that's kind of what we see. Like if you look in the direction of the constellation Orion, there is, right below what's called the belt of Orion, there is a stellar nursery where stars are currently being born. And so there's this giant gas cloud, huge. I mean, it's many light years across. And we're seeing, hundreds, in fact, even thousands of stars that are being born from this gas cloud. So our sun very likely was born with lots of other stars, or lots of other star systems. Probably, if I had to guess, maybe 100, maybe 1,000 other stars. All right. Anyhow, all right. So this is just more of the inner planets, the being rocky worlds, the outer planets being gas giants, right? Made mostly of hydrogen and helium. Which, of course, but by the way, the hydrogen and helium come from the Big Bang itself, all right? Which we haven't really talked about much in this class, because we're talking about planets for the most part. But the Big Bang happened about 13.8 billion years ago, and that's when all the hydrogen, all the hydrogen and most of the helium was created. And what stars do during their lifetime is they're fusing. It's a nuclear process. They're fusing and turning hydrogen into helium. So there's always a little bit more helium in the universe as time goes on. All right. So anyhow, let's keep going here. So there's the ice giants. Just to let you know, when we get to these exoplanets, Neptune-sized worlds seem to be the vast majority of exoplanets that we find out there in our galaxy. Let me place it that way. So when we look out at all right, let me just look at this real quick. All the stuff within the solar system is formed from the same stuff. There's the age of the solar system, 4.5 billion years ago. All right, so this is just the theory of planet formation, and it actually, people have been thinking about this for a long time. This goes back to the 18th century, right? So there was a French mathematician named Laplace. This guy was a German philosopher, and they were thinking about the formation of the solar system even back then. And so they